Uh, okay, I'm Sasha Ebanov. I'm Deputy Director of Simon Center for Geometry and Physics. I'm happy to welcome all of you to the center. Some of you have been here and some of you were not here before. So let me introduce first the series of lectures and then the speaker. So we have benefactors, which are Della Pietra families, who generously support our outreach activities. And in particular, there is a series of lectures, which is called Della Pietra Lectures, which allow us to bring distinguished speakers from all around the world to give lectures on topics of physics, mathematics, or other sciences. And our series consists of 3 lectures. One is a public lecture for general public, which happened yesterday, for example. And one lecture is high school students lecture, so for which we bring high school students from local schools. And one more is a more technical colloquium for physicists and mathematicians. Still broad colloquium lecture, but already for more specialized audience. And thanks to this generous support, we can bring really distinguished, really distinguished speakers from everywhere to the Simon Center. And we are really happy to have Cumrun Vafa today as our speaker. And Cumrun is a visionary and leader in string theory and quantum field theory in general for many decades, well, several decades. And he's a Harvard professor, Hollis professor in mathematics and natural philosophy. And Cumrun is known for a lot of discoveries, starting from rigorous theorems to broad visions of string theory, quantum field theory, etc. And it's very difficult to talk to people who did not study math for many years about these subjects. They are quite abstract. And therefore, we're especially happy because Cumrun written a book recently, which is this book, Puzzles to Unravel the Universe, where he's trying to at least convey some concepts which are used in modern physics, very abstract and very complicated physics, but some very transparent ideas, and he will talk about this today. And we do encourage you to interrupt at any point with questions and remarks or comments, whatever you want. This should be as informal as it is possible. And please welcome Cumrun Vafa as our speaker.
Thank you. Thank you, Sasha. Thank you, Sasha, for the kind introduction. It's a great pleasure to give this lecture here. Actually, I have to say, among the 3 Della Pietra lectures, this is my favorite one. And I'm happy to be able to do that here today with giving you a presentation on a topic which is very dear to my heart. And that is basically trying to describe physics, bring it down to this bare bones of what it is about without getting to technical stuff. And so here, I want to exemplify that using mathematical puzzles. So in fact, many deep ideas in physics have simple origins. You know, sometimes you look at these physics things and they look very complicated formulas and kind of, it doesn't look very easy to follow or what is going on. But really, the ideas underlying them are simple. And if they cannot be explained in a simple way, then that means it hasn't been understood well enough. And that's not that your problem. It's the problem of the person who's supposed to be able to understand it clearly enough to say what is it trying to say. Now, it sometimes might take a long time to actually say that in a simple form, but some things we can say in a nice simple form, and many of them are exemplified by simple mathematical puzzles. So, in fact, this was the motivation for me in trying to set up a freshman seminar course at Harvard, where I did exactly that. Namely, I had the course where I used mathematical puzzle to basically explain physical principles and its connection to mathematics, and basically covered old principles in physics and modern ones, and give examples from all these different things, which led to this book that Sasha already mentioned, Puzzles to Unravel the Universe. Actually, pandemic gave me a time to actually finish the book, which is a situation that's consistent with what was going on in the past few years. So this is the book. And I'm going to talk today about some of the puzzles, like about 100 puzzles or so in the book, but I'm going to just take a sample of them and just going to discuss some aspects of them. So math and physics have had a beautiful history of interaction over thousands of years, and perhaps one of the first strong interactions between math and physics is in the context of Greek mathematicians and philosophers studying both mathematics and nature. They were trying to explain how nature works, or at least how the basic elements they perceived are important in understanding nature, and connecting it to geometry and to symmetries. So they, for example, imagined that there are 5 basic elements in the nature: air, earth, fire, water, and the universe. And they were trying to associate these 5 elements to 5 Platonic solids they had discovered as being particularly symmetric objects that they could understand and construct. So they were trying to connect math and physics from early on, and this is an example of it. This attempt was not very successful, as we now know, but the motivation was there from the beginning. These ideas continued with the work of different people in different cultures: Chinese, Indians, Muslims. Everybody was trying to move it along in different times, one culture, the other one, and they were kind of pushing it gradually towards deeper understanding. For example, Biruni measured the radius of the Earth by going on a mountain and looking at the horizon and looking at the angle it makes with the angle it makes with the vertical line to measure the radius of curvature, knowing the height of the mountain, radius of the Earth. So those using simple geometry, for example. Or, in fact, let me ask you a question before I show the next slide. How many of you know what is the height of the atmosphere, roughly? Well, yeah, something around that range, exactly. When was that measured is my next question. How many of you think it was measured a century ago? You can raise your hand if you think it was a century ago up to now. And was it a recent discovery? How many think it was discovered maybe 500 years ago? Okay, how many think it was discovered 1,000 years ago? Okay, so 1,000 years ago, some of you think it was discovered. How do you think it was discovered 1,000 years ago? Anybody? Did they go up there and just see where the air is finishing up? No, I don't think so. How did they come up with the height of the atmosphere? Now, this sounds like quite modern, like, right? And we go out there and you take a picture. You say, oh, you see this blue thing around the Earth? Yeah, that's the atmosphere and so on. But that's not how they did it, of course. So how did they do it? The idea was actually quite simple. And again, geometry. And this was the idea. So they say, okay, we are here, let's say, on the Earth. And suppose there's a sunset. The sunset is when the light ray is tangent to the surface of the Earth. So as soon as the sun goes beneath this line, then you wouldn't see the sun, and that's what we call sunset. Suppose the sun goes further, but even after the sun is down, the sky is not immediately dark. There's no sun, but it's not dark, right? We all know that. But why? Well, they reasoned that the reason it's not dark is because there's some of the light of this sun, even though it doesn't get to us, it gets above us to the sky, above, to the air above us, and it lights it up. And then they said, okay, when is it going to be completely dark? Well, it's going to be completely dark if the last ray of sun cannot get to the air just right above you. Then the sky above you will look dark. So in other words, the time span after the sunset and before the sky is totally dark is a measure of what is the height of the atmosphere. The higher the atmosphere is, the longer that's going to be. So just by measuring and checking out how long it takes for the sky to get dark, which we all can do, a couple of hours maybe, and knowing the radius of the Earth, which they had measured different methods, they estimated the height of the atmosphere. So the point here is that simple geometry, nothing too fancy, can lead to these things with common observations, nothing exotic. More advanced connections between physics and mathematics had to wait till the times of Newton, where he invented a branch of mathematics, calculus, to try to describe how projectiles move and what's the laws of mechanics of objects. So this is These are summarized in what we call the Newton's laws of motion. And a couple of centuries later, Gauss tried to, he was a mathematician and he was trying to understand aspects of mathematics, but he was also interested in physics, and he and other mathematicians discovered that Euclidean geometry is not the only kind of geometry. Like in the Euclidean geometry, the angles of a triangle add up to 180 degrees, but there are other geometries that if you draw quote-unquote straight lines, the angles don't add up to 180 degrees. And it could be more or less than 180 degrees. And that's the notion of having curvature in space, which mathematicians came up with. And he was asking questions like, could it possibly be that if you go on top of 3 mountains and look at the light ray coming from the peaks of the other 2 mountains, and you form a triangle that way, would it be that if you add up the angles of those 3 angles that you get, would they add up to 180 degrees or not? And well, the measurement at that time would not be enough to measure it because it's going to be very tiny, but we now know that it doesn't add up to 180 degrees. So it's not exactly Euclidean geometry. So the space that we live in is not quite Euclidean. Maxwell, a physicist, was trying to understand electricity and magnetism, but he needed to use differential calculus, again, a branch of mathematics, to formulate the laws of electricity and magnetism. I mean, he had these equations. I'm summarizing the form of the equations in a form which may not be familiar to you. But anyhow, he wrote the equation in some form of a differential calculus, some equations, which actually he needed to modify for it to work because the equations, the math equations, were not consistent with each other. He had to add a term to one of the equations, and it kind of looked like a fudge factor. He put it there to make it work. And he said, oh, if you add that term, you get new solutions, which are waves moving with the speed of light. I said, maybe that's light? So this mathematical consistency motivated him to think that maybe the light we see has something to do with electricity and magnetism. Very strange idea, but that's, again, consistency of math led him to this kind of a physics prediction. And then a mathematician, Riemann, was interested in geometries in our space which involve curvature of space. He was trying to see if that has to do with forces again. So this is again the old idea of can I connect geometry with physics? But he didn't have the right tools, and it had to wait for the work of Einstein, where he combined 3-dimensional space and time into 4-dimensional space-time, and came up with what we call application of Riemannian geometry in physics, which is general theory of relativity, which basically describes how gravity works in terms of geometry. Namely, if you have a planet like Earth, it curves the space around it, and that curve makes objects around it go in funny paths, which we call orbits. So the curvature of space and time is actually another way of saying what is happening to the force of gravity that Newton was talking about. So again, connection between geometry and physics. And then later, last century again, Kaluza and Klein suggested that maybe we have extra dimensions. Like we have 3 space and 1 dimension. If you have 1 extra spatial dimension, like a circle, if at each point you have an extra circle, then that theory could actually accommodate not only gravity, but also electricity and magnetism together in a unified form. So a 5-dimensional geometry encodes both electricity and magnetism and gravity in 4 dimensions. So you can convert forces in 4 dimensions to geometry in 5 dimensions. So it unifies different pictures. So as you can see, the connection between geometry and physics, or mathematics and physics, has been going on for many, many years, and it's kind of getting more and more mature as it goes along. And this brings me to the area that I'm working on, which is called string theory. And so the aim of string theory is to unify fundamental forces and particles into one framework. And it aims to talk about physics at the smallest scale, much smaller than an atom, to the whole universe. So it covers the whole spectrum of length scales. And the basic postulate is that the fundamental particles are not point-like, but extended objects like strings. So for example, if you think about the proton, which we think is made of 3 quarks, point-like quarks, but actually we think that these quarks may not be quite point-like, and if you zoom in, there might be structures like strings, tiny little strings, which are too tiny to discern with the everyday experiment, they look like points, but if you just zoom in, then you see a tiny little loop there. And that is basically the idea of string theory. Now you might ask, why? Why would you do that? Why would you replace a particle with string? What is so special about string? Well, it turns out it resolved the inconsistency that exists between quantum theory, which is one of the pillars of physics, modern physics, and Einstein's theory of gravity. So these two pillars had conflict, and this string theory resolves this conflict in this context. And the interaction between strings are very simple. You're just seeing the interaction. Two strings come, they kind of join and make one string, right? It's very simple. And that underlies all the forces, electricity, magnetism, gravitational force, every kind of force that you have comes from this kind of diagram. And in joining, and also the reverse of it as well, splitting, namely a string going down and splitting to two strings. So this is the interaction between strings. And this diagram, guess what does it look like? Pairs of pants. And actually, this is called the pairs of pants diagram in physics. So the pairs of pants diagram underlies all the forces in the context of string theory. Very simple when you think of it this way. So the area of the research that I'm working on is, as I said, string theory, but it's very mathematical. And in fact, it is more than what I have told you. If you take three-dimensional space, it turns out you need 6 more dimensions. 3 is not enough. You have to go 9 spatial dimensions and 1 time. And these 6 extra dimensions, you might say, where are they? I don't see them. Well, we see 3 big ones around us. And these other ones must better be tiny and difficult to see. So something like a picture like this, that at every point in space, you could kind of imagine 6-dimensional spheres or tiny crumpled spaces that we don't know what exactly they look like to be there at each point. And everyday experiment that we do kind of averages over them. So we don't see that. We just see the bigger ones. So as I said, the aim of my talk is to not go through these complicated math kind of things, but explain some of these basic ideas in physics, not just in the context of string theory, but more broadly in the whole physics. How do they relate to simple ideas? How do you see mathematics as mathematics kind of explaining some of these basic principles? And the idea of this in this context that I need your help. I'm going to ask questions that you will hopefully help solve puzzles together. So that's going to be rather interactive. And so please feel free to ask questions and interrupt and all that. If there are any puzzles that I'm saying is unclear or something, just slow me down. So the first topic I want to talk about is symmetry and conservation law. Okay? We start with 2 pints of paint, one green paint, one white paint. We fill it, a glass with the green paint, and we pour it into the white paint. And we stir it. It's important we stir it. And then we take the same size from the mixture and put it back into the green paint. And then again, stir it well. Okay, everybody know what we just did, right? Green and white were separate. We took 1 cup and put it from green to white, mixed it, and then take the same amount back from the mixture to the green. Okay, so so far so good. And what we are asking here is, which container has the higher concentration of the other color? Does the green have more white mixed with it, or the white has more green mixed into it? Is the question clear? How many of you think the white container has more green to it? Raise your hand. How many think that the green has more white in it? Raise your hand. How many think they're equal? Raise your hand. Okay. So almost all of you, except for a few, said that indeed the white has more green, and that is the intuitive answer. So let me explain why that's the intuitive answer. Probably you already have the reason, because that's why you answered it that way probably. The white has more green into it, you might think, because you take a pure green and put it into the white. But when you mix it, you're getting it from the mixture. So some of the green is going to go back to the green container, and therefore it's going to be the white is more green than green has white. That might be one kind of reasoning that might lead to that. But actually, the answer turns out to be they are all both equal. It is very surprising. Intuitively, you would think, what was wrong with what I just said? It sounded like a reasonable statement. So let's just see why symmetry and conservation of mass explains that they have to be equal. You see, you started with equal amount of green and white paint, right? Equal amount. Whatever you shuffle or not, the total amount of green at the beginning and at the end are the same. The total height of the paint at the beginning and the end were the same. So whatever is missing from that green container must be on the other side because the total green doesn't disappear. But also by symmetry, whatever there is white must be other way. So they must have just switched by just the conservation. In other words, if you think of it like this, just suppose you unmix them. Whatever is missing from the green is on the other side, and whatever is missing from the white must be the other one. They must be equal because the volumes were equal to begin with, and the volume, the mass doesn't disappear. So by symmetry and conservation law, they are equal. So it's very strange, but it's true. So symmetry and conservation law somehow explain and deconfuse us in this case. Let's go back to Greek philosophers. Aristotle. He thought heavier objects fall faster than light objects. Stands to common sense, right? If you have a heavy stone and a tiny pebble, you drop them, you would think the heavier object falls first. How many thought that way? I thought that way, but how many of you thought that way before studying it, perhaps? I don't know. Yeah, so it seems like a natural thing to think about it that way. For some reason, that's our mind goes, maybe we are worried about this heavy object hitting our foot or something. Anyhow, we are more concentrating on the heavier one. Who cares about that light pebble or whatever? But Galileo said no, all objects fall at the same rate. In fact, he did experiments by going on Pisa Tower, dropping stones with different sizes and finding that they fall at the same time. Now, of course, this is true only if you ignore the air resistance. Like we're not talking about the feather kind of, which is by air resistance kind of goes the very slow path. That's not what I'm talking about. So we're ignoring the air resistance. So ignoring that, they should fall at the same rate. And this was more or less consistent with what he was seeing in experiments. So when he told this to the scientists at his time, they said, what, you did experiments to do this? Experiments? No, you have to explain why it's true. So at that time, science was not very experimental. Not like our days that you have to do experiment only to really get moving in science. There it was a different atmosphere. So he had to come up with a good kind of reason to convince people that this is the right answer. And so the way he argued that this is the right answer was using symmetries. And the symmetry argument had to do the following. He said, consider 3 bricks, same size, same mass, everything, same shape. Put them at a given height. Put them at a given height and then release them at the same time. What's going to happen? Well, let's see. They fall to the ground and hit the ground at the same time. Not too fancy, right? Of course. Why do we know this? Well, because of translation symmetry in the horizontal direction. If you move the brick from horizontally, nothing is changing. You can just shift over. And the brick is the same size, same mass, so same time. So why shouldn't they fall at the same time? So symmetry tells you that they better fall at the same rate. Is that clear? Okay, then he asked the next question. He said, well, suppose I move around the bricks horizontally. Does it change the answer? Like if I went instead like this, and then I dropped them. Would it change it? They said, of course not. Symmetry. Don't waste our time, Mr. Galileo. Move on. This is obvious. We know that. The symmetry is, so, okay. So let's do another question then. Suppose we move them a lot, like move them around so that 2 of them are touching and then the release. Does it matter? They said, no, of course it doesn't matter. They fall at the same rate. So, that one is twice bigger than this one now, and you said it doesn't matter. They fall at the same rate. So an object twice as big as the other one falls at the same rate. So just by this simple kind of mental gymnastics, he undid their confusion. And so this is what physicists love to do, namely to understand the basic reason of something, why it's working the way it does. And this is the way Galileo tried to explain this fact, which is counterintuitive. Now, symmetries are fun, but what is even more fun is breaking them. Not breaking them with hand artificially, but what we call spontaneous breaking of a symmetry. So let me give you a puzzle related to that. We have 4 cities, A, B, C, and D, in the 4 corners of a square. We are trying to design a highway system which connects all cities together. We want the total highway length to be minimal. Is the question clear? Total highway length to be clear, and we want to connect to be able to go from any city to any other city. Not necessarily direct path, but some path. Okay, is that clear? Any questions about the puzzle? What is the best highway system that we can design? How many of you think this is the answer? Raise your hand. Very interesting. How many think this is the answer? Raise your hand. How many of you think this is the answer? Raise your hand. Okay, I guess you guys are not convinced any of these are answered. In fact, this is not the answer either, and it turns out this is the answer. This is a bizarre looking answer, right? I mean, what is this? This is a place where the road kind of splits to 3. Here we have 3 of the angles here are all equal to 120 degrees. And they kind of meet that point and go like this. Now, why is this unintuitive? Can anyone tell me why this is unintuitive? Any of you? What aspect of this is unintuitive? Yes? That's one aspect. The middle part is kind of like is hanging there, but yes. Is there any other aspect which is surprising in this answer? Yes? Yeah, so that's also bizarre. Is there any other angle? Is there any other? Why would we have naively assumed an answer like this at the beginning? What is the difference, kind of like this answer and let's say this answer? Yes? None of them quite directly, but the first one has some extra feature. What feature does it have? Yes. It is 1 point. It's the most symmetric too, right? You have a kind of like, it has the same symmetries as a square. If you rotate it like, if you have a square, if you go like that, it looks the same. It doesn't change. But this one does not have the symmetries of the square. So for example, suppose you lived in city A, and one of your friends was in city B, and another friend was in city C. The friend B and C are equal distance from you in terms of actual physical distance, because they are both on the corners of adjacent corners of a square. But the distance in travel time from A to B is longer than from A to C. Right? We have broken the symmetry. The symmetry of trying to get to A to B, you might have thought it should be the same as A to C, and that's not the case anymore. So this is what we call spontaneous symmetry breaking. Namely, the problem you started with had a symmetry. City A and B and city A and C were the same distance from each other, but the highway system connecting them were not equal distance anymore. And it's not because we had a bad design for the highway. This is the best design, and the distances are not equal. In fact, you might think that there's another design you can make, and that's true. You could also first connect A and B and then go down and then go C and D. So A and B would be then closer, but still A and C and A and B will be different distances traveled from one to the other. So no matter how you cut it, either this or the flipped version, you have broken the symmetry spontaneously. Any questions? So the early Greek philosophers also thought Earth is round and that it's at the center of the universe. And it's not moving. So they had already figured out the Earth is round by noticing that the shadow, if you have a stick on the ground, the shadow of it at noon, if you're on the equator, is 0 length. But if you move up north of equator, then the shadow increases proportional to how far away you move from the equator. And by seeing how much the length of the shadow grows as you go farther north, they figured out the radius of the Earth. They measured the radius of the Earth. So they had already some understanding of why Earth may be round. And they were looking around them, and they would see the moon. The moon seemed to move around. The sun seemed to be moving around. These planets seem to be moving around. So they said, why isn't the Earth moving around? The Earth seems to be still. Okay? So that was their big question mark. Why is the Earth not moving. They thought Earth being spherical must be at the center of the universe that's not moving, and that's the reason. The reason is that being at the center of the universe is consistent with the symmetry, but if it moves in any direction, you have to pick a direction. And as soon as you pick a direction, you break the symmetry. So they say this doesn't happen because symmetry cannot be broken. It breaks the symmetry. Therefore, the Earth doesn't move. Is that clear what their argument was? Now, so you might think, wow, this is a funny argument. We know we are moving, so what are they talking about? Well, we're not at the center of the universe and all that, but this reasoning sounded kind of possibly correct, except that Aristotle said this is not a good argument. And again, Aristotle comes here now to say what is the right argument and try to convince them that this is not a good argument. He says, well, suppose you have a person and you put the person at the center of a circle and you spread food around the person, like loaves of bread, on a circle around the person. What do you think is going to happen? Do you think the person is going to stay there forever, or is going to move to grab some food when he gets hungry? Indeed, after a while, the person is going to break the symmetry and choose a point. Which direction you go on the circle, he wouldn't care. He would just choose one point and just go and get the food. So therefore, breaking of the symmetry is very natural, because sometimes it's optimal. It's better to break symmetry. It turns out that these same pictures, well, maybe with loaves of bread replaced by minimum energy, appears in modern physics. Exactly this picture. If you replace a loaf of bread with a minimum of a potential, explains why what we call the Higgs field wanders from the middle all the way down to the periphery and breaks the symmetry. It turns out that field is the distance that field moves away from the origin is proportional to the mass of the electron, mass of the proton, and mass of things that we see. And so therefore, it gives mass to everything. So therefore, the Higgs particle gives mass to things. And that's what is the origin of, I think I went too fast here. Yeah, okay. Before I say that, I have to show you something. So the guy moves, of course, we discussed, but there's actually more to the story. Every one of us have broken the symmetry by our body. What do I mean by that? Well, we live on the Earth, and Earth on the average has 360-degree horizontal rotation symmetry. You can rotate around, and generically all directions are the same. Of course, I don't mean if you're next to a mountain or ocean, it won't be the same. It won't be the same there, but on the average, it's the same in all directions. So you would think that our body should reflect that symmetry. Like, we should have eyes all around our head, 360-degree rotation symmetry, like the one I was just showing on the other one, like this one. You should have like this. Of course, we don't have like that because somehow the symmetry has been broken on our body. Why do you think that is? Well, evolution must have decided it is not economical to have so many eyes. It's just to have it in the front is good enough. Why? Well, maybe it's related to what Aristotle was talking about. You want to see where the food is and to go after the food. You don't just need to where the front is. You don't need all over it because you cannot move in all directions at the same time. You just go in one direction, and that's why you need to know which direction to go. That's why you have eyes in the front, not all around you. Now, that might also explain why the trees, on the average, are more symmetrical, like circular. Trees do not have a front and a back, typically. So that is consistent with the fact that trees don't move. So the movement, the motion, is what's related to that spontaneous symmetry breaking phenomenon that we see. So spontaneous symmetry breaking has many applications in physics. I told you one of them, which is the origin of the masses, the Higgs particle. But there is more to it. For example, you see we are made of what is called matter, but there are other things called antimatter. Antimatter and matter annihilate. It's not just science fiction. Every matter has an antimatter which can annihilate to nothing. Now you might say, where were the antimatter? Well, there were a lot of antimatter at the beginning of the universe, and they essentially all canceled the matter, except there was a tiny asymmetry between matter and antimatter because some spontaneously symmetry breaking happened. There was just 1 in a billion more matter than antimatter. all the matter, antimatter annihilated except that 1 in a billion, which we are made of. So we are out of the luck of that 1 in a billion there already. Spontaneous symmetry breaking again. Other things, magnets. You know, these cool magnets, the ferromagnets you may have played in when you were even a kid, again related to spontaneous symmetry breaking phenomena. Superconductors, another phenomena. So these are all examples where symmetry breaking plays a key role. So here I want to give you some power of simple and abstract mathematics. Can one use mathematics in simple ways? And here now I want to go back to some simple ideas that you have seen, I'm sure, at even elementary grade. So let's go back to some simple math. Now the idea is simple, but I don't want you to use math. I want you just to guess the answer to this one. So consider having Earth and the equator. So this is the equator. And suppose you wrap a belt around the equator, and you open up the belt, and you add 1 meter to it. So this is the belt with 1 extra meter added on top of it. And then you wrap it around the Earth again. Wrap it around the equator. Now it's going to stand a little bit above the ground. Question is, by how much? How many of you think it's going to be more than a centimeter? Raise your hand. How many think it's going to be less than a centimeter? Raise your hand. Well, it's going to be either this or that. I hope one of you raise your hand in either one. If you're not sure even, just guess. It's okay. I know that you can sit down and calculate, but I'm not asking that. So again, let me ask the question. How many think it's going to be more than a centimeter? Raise your hand. Okay, like 10 of you. How many think it's less than a centimeter? Raise your hand. Okay. So the majority of you think it's going to be less than a centimeter, and that is, again, a common sense answer. But let's see what it is. We can do the calculation. The circumference of the Earth is 2 pi times the radius of the Earth. So that's the original answer. You added 1 meter to it. So the new length of the belt is 2 pi r plus 1. Now, that is going to be the new circumference. And the new circumference is 2 pi times the new radius. But the new radius is nothing but r plus this extra little x. So 2 pi times the new radius should be the old circumference plus 1. So you say 2 pi r plus 2 pi x is 2 pi r plus 1. The 2 pi r cancels the 2 pi r. You just get 1 is 2 pi x. And therefore, x is 1 over 2 pi. In other words, around 16 centimeters or so. 1 meter over 2 pi. 2 pi is like 6, so it's like roughly 1/6. So 16 centimeters. That's unintuitive, right? But this is simple math. Elementary grade math. Just circumference of a circle. That's all. But somehow we made a mistake without using math. Why? Well, the reason is that our intuition is viewing the lengths in a ratio sense. We are looking at the x compared to the radius of the Earth. And in comparison to r, to the radius of Earth, x is tiny. So that confuses us to think the actual length is tiny, which is not. But let me ask you a further question. Suppose you take the circumference and this belt and so on, but instead of just putting it uniformly around the equator, suppose you pull one side. Suppose you pull one side of the belt. So it's wrapped tight around the other side of the Earth, but around where you're pulling it up, it's maximally pushing up. This way you can pull it a bit farther up. Is that clear? Question is, how much do you think we can raise it now? We can raise it more than 16 centimeters now. How much? How many think it's going to be half a meter or less? How many think it's going to be 1 meter or less? Raise your hand. How many people think it's going to be more than 100 meters? Raise your hand. Huh, nobody did. Okay. Well, the answer turns out to be 121 meters. This is shocking. This is totally shocking. We're adding 1 meter to the length of this belt, and we are pulling one side, and you can raise it 121 meters. So this one is a little less elementary math because you need a little calculus. So therefore, I'm not going to show you here. But again, it means that you need to do some amount of mathematics to actually see these kind of pictures. So in mathematics, one of the fun things is, or simple basic principles of topology is continuity. And this also is very much relevant for physical laws. So consider again, let's go back to the equator. Suppose we measure the temperature on the equator. Physical quantities typically vary continuously as you go around. It doesn't jump around. If the temperature is 15 degrees here, over here is 15.1 maybe, over here is maybe it's 14.9. It doesn't just like go from 15 to 80 suddenly. It gradually moves around. That's what we mean by continuity. So the question we're asking here is the following. We consider the temperature around the equator. How many of you think that at any moment there are 2 points on the equator diagonally across relative to the center of the Earth which have exactly the same temperature? So let me repeat the question again. How many people think that at any moment there are at least 2 points on the equator diagonally opposite relative to the center of the Earth which have exactly the same temperature? How many people think the answer is yes? Okay. How many of you think no, it may depend on how the temperature varies around this equator? Okay, so roughly half-half think one way or the other. And the answer turns out to be, perhaps surprisingly, that there always are at least 2 such points. And that for which the temperatures across from each other are equal. And to see that, you consider the temperature on opposite points and consider the difference between the temperatures. Let's define a function which is the difference between the temperature here minus here. If this is 0, if this function is ever 0, we are done, because that's what we want. We want to have a point for which the temperature and the opposite temperature are equal. So the question is, does this function have to have a 0 or not? If this has to have a 0, we are done. Suppose it's not 0 at one point. Choose a random point. Suppose it's not 0. Let's say it's positive. That means this temperature is higher than this temperature, right? Now suppose we gradually move the point that we are looking at and look at this temperature minus this, this minus this, this minus this, until we get to this point and we consider this minus this. If this was higher than this is lower than that by the same amount. So in other words, the difference is now opposite sign. In other words, if this t minus this one was positive, now this minus that is negative. So the function flips sign when you go around from one side to the other. Is that clear? So you have a situation where the function goes from one value to the opposite value. And if some function goes from a negative to positive in a continuous fashion, and it cannot jump, in other words, it has to cross 0 somewhere, at least once. And that means that there must be a point where, at that point, the temperatures are equal on opposite sides. So this is the application of continuity. How many of you think that the same is true for pressure? That is, suppose I measure the temperature and pressure everywhere on the globe and ask you, are there at any moment 2 points on the globe exactly diagonally opposite relative to the center of the Earth for which not only the temperature is the same, but also the pressure is the same? How many of you think the answer to that is yes? Raise your hand. Okay, how many think no? Okay, so indeed the temperature and pressure at every moment, there are at least 2 points for which the temperature and pressure are exactly the same, again, by continuity arguments. So some features like this are driven by topology of what we call topology of the situation, and in this case, it's driven by what we call continuity. So that's the situation I just described, temperature and pressure being the same. Now I want to talk about another example, and this is what's called the gravitational lensing. Gravitational lensing is a phenomenon which has been observed, and it's really cool because imagine when you look at the star, you say, oh, there's a beautiful star there, oh, look at that star there. Could it be that the few stars or galaxies or whatever you're looking at are the same? Could it be that you say, oh, that galaxy and that galaxy, no, they're the same? Of course not. What can it be? How could it mean? You're looking at 2 different things. Gravitational lensing says, no, it could be the same. You're looking at that one and that one are the same? Yes. How could that happen? Well, in Einstein's theory of relativity, light bends. So if you imagine starting from a galaxy and looking at two paths of light that's coming to you, here we are at Earth, if the light is coming to you one way, if it bends by the matter in between, maybe some bigger galaxy somewhere or some other stuff in the middle, when the light bends and gets to you, when you're at the Earth and looking at it, you say, oh, there's this galaxy, oh, and then there's this galaxy. So you see two different paths that are coming at different angles. So you might be confused and think, oh, yeah, two different galaxies. But they're the same galaxy. So this is called gravitational lensing because the effect of the matter in the middle is like bending the light, just like the lens does. So, in fact, here, in this picture, you see all these objects, right? This is an actual picture of the sky, not taken with the regular camera, of course. These are, each one of these little things are a galaxy. So this is really refined, and these blue ones are quasars. Quasars are like old galaxies. So you have galaxies and older ones, which at the beginning of the, very close to the beginning of the universe, there were these very shiny objects which are called quasars, and they were basically galaxies. So there are different kinds of galaxies. Actually, it turns out in this picture, 5 of these quasars are the same object. You're looking at the same object. And 3 orange ones that you're looking at are the same galaxy. We are being fooled. So if we looked at that picture, we would have been totally misled to think we're looking at different objects. So this is the bending. What ends up happening is that the number of images that we get, the number of images that we see, turns out to be always an odd number. You either get 1 image, 3 images, 5 images like these, 7, etc. You don't get even images. You get always odd images, unless, of course, you block a light. In other words, you can, of course, block it, and then you get less images. So let me ignore blocking the light by hand or by some falling into a black hole or something. Let's just assume all the light gets out. In that case, you get always an odd number of images. Now, you might wonder why. In fact, more is true. You get odd number of images, and exactly slightly less than half of them are flipped. In other words, it's like left-right flipping happening. They're inverted. So for example, you might have 5 images, like here, these blue galaxies, blue circles, and 3 of them are the regular orientation, and 2 of them are actually flipped. You might see, wow, this is fancy stuff. How do we actually prove it? You might think you have to solve complicated Einstein's equation and this and that to show these facts. And this fact that is the odd number of gravitational images turns out to be as simple as the continuity argument I was telling you about the temperature on the equator. We can explain that why the images are odd and why less than half of them are inverted by the same kind of reasoning. So to do that, this is going to be probably the most fancy math I'm going to tell you today. So you may not follow all of what I'm going to say this part. So excuse me if I say this one, but I just want to illustrate a little bit about some slightly more advanced math, but still related to the same basic notion of continuity. We'll explain why. And to do that, we have to define the degree of a map. The degree of a map. If you have a map from a space to another space, the degree of a map is the number of pre-images of a given point. So if you have a map to a point, you say how many points got to that point, and you count the different ways to get that. You call the number of pre-images, you call the degree of the map. But if you count the degree of a map with a plus and a minus sign, it turns out that that number does not depend on which point you chose on the image. The pre-images, if you add with a plus or minus sign, where the plus or minus sign corresponds to whether the orientation flips or not, is something that does not depend on which image you chose. So now let's consider the following. Suppose this is our galaxy here, and you're over there somewhere on Earth. Consider a small sphere around the galaxy, and consider a massive sphere centered at the galaxy, but now passing through us, let's say somewhere where the Earth is. Is it clear? So we have 2 spheres. One is, both are centered at the galaxy. One is near the galaxy, centered at the galaxy. One is still centered at the galaxy, but huge and passing by the Earth, somewhere there. Is that clear? Okay, suppose there's no matter between us. What's going to happen? Well, the light rays coming from the galaxy go straight lines, right? Nothing fancy. So every point on the sphere where the light hits will get, that same light will hit the same point on the corresponding point on the bigger sphere. So you get, in this way, a function, a map, from a small sphere to the big sphere, basically by following the light. In this case, just straight line. Is that clear? What is the degree of this map? In other words, what is the number of pre-images of every point? It's 1. Every point on that bigger sphere will get mapped exactly by 1 light ray passing through the corresponding point on the smaller sphere. So we say the degree of this map is 1. Is that clear? So I just told you that if I have a galaxy and a small sphere and a big sphere, the degree of that map is 1 if there is no matter. Now suppose you populate the matter in the middle by turning on mass on the galaxies, gradually building up galaxy in the middle and so on. The degree does not jump, it's continuous. So the degree was 1, and it cannot suddenly jump to 2, 0. No, it cannot, because of continuity. Degree is a continuous function. So no matter what happens, the degree is 1. Okay, does that mean the number of pre-images is always 1? No. It means the number of pre-images, the net number of them is 1. There could be plus or minus, depending on the orientation, that could flip. And so the total sum of number of pre-images up to signs, which correspond to orientation reversal, is 1. And that's why we always will get an odd number of images, such that less than half of them, exactly less than half of them, have a minus sign next to them, so that when you add them up, you get plus 1. So if you have a 5, you get 5 is equal to plus 3 minus 2. 7 is plus 4 minus 3, and so on. So the minus corresponds to the inverted one. Perhaps a good way to illustrate it is in this picture. If you think about the Earth and the galaxy here, you can, instead of making the ray being bent around, you can twist the geometry around the star to be twisted around, and you can see the number of ways that the number gets to the Earth will change depending on which light ray it goes. But you see it's always 5, 3, 1, etc. And the sign goes back from plus to minus depending on whether the direction that you're going is in the same sense as the light that you're getting, or the opposite that you're getting through. So this is the orientation reversal. For example, here you have 3 pluses and 2 minuses, giving you a net plus 1. Now, I want to show you more power of mathematical abstraction, and this is the puzzle related to that. We have 4 ants moving at constant velocity on the plane. They collide pairwise, but they continue their path. And the question you're asked is, if all pairs collide, does also the last pair have to collide or not? Is the question clear? Let me repeat. There are 4 ants moving at constant velocity. Doesn't mean they have equal speeds. They have different speeds and different directions. In fact, no 2 of them are going parallel. They're all going to have an angles. And we know that out of all pairs, all collide except potentially for 2 of them, ants 1 and 2. Do ants 1 and 2 also have to collide? How many of you think the ants 1 and 2 have to collide? Raise your hand. Wow, okay. How many think they don't have to collide? Okay. So it turns out that they actually do have to collide, as most of you guessed. And how to see it, though, is not necessarily that obvious. Does anybody know how to see it? It's not necessarily easy. In fact, this is the case where we need abstraction. This problem is 2-dimensional, like we have ants on a plane, right? But actually, is it 2-dimensional? Is this 2-dimensional problem? Does anyone think it's 2-dimensional, may not be 2-dimensional? There is time. There are 2 space and 1 time. So it's 3-dimensional problem. If you think about the plane and add a time axis, then it looks a little different. So we, just like Einstein's theory, he added 3 space and time together. It turns out you can solve this puzzle by thinking of time in addition to space. So how does that help you? Well, if you add a time axis, what does that mean? As the ant is moving, you have to put the ant where the corresponding time is. So you get a straight line. For every ant moving, you get a straight line in this 3-dimensional space. The reason it's a straight line is that we assume they go with a constant velocity. So each ant gives you a line. Is that clear? What does it mean that the two ants collide each other? Anybody? What does it mean about those lines? They intersect, exactly. So you have 4 lines, each ant has 1 line. So there are 4 lines in 3 dimensions. Now it's becoming, sounds like geometry. 4 lines in 3 dimensions, and they pairwise intersect one another, all of them except potentially 1 pair of lines. And we're asking a question, does the last pair of lines have to collide, intersect or not? Is the question clear now? Formulated that way, now it's going to be easy to answer it. So in other words, we basically add this time dimension to the game by tilting the time, basically. And as the ants are moving, they're moving on, you can think about it as if they're moving in time like this. And we're asking if 1 and 2 have to collide. So look at these geometries. So we're asking about whether 1 and 2 will collide, and they will collide. And the reason is this. If you look at this picture, the line 2, line 3, and line 4 should form a plane. Why is that? Because they all intersect each other. So 2, 3, and 4 are on the same plane. On the other hand, 1 and 3 and 4 also collide. So 1 and 3 and 4 are also on the same plane. So in other words, line 1 is on the same plane as the 3, 4 lines, as well as the line 2. So both lines 1 and line 2 are on the same plane, spanned by lines 3 and 4. Now, if they were parallel, they could potentially not meet, but I said they are not parallel. Therefore, if you have 2 lines on a plane, not parallel, they're going to meet. They're going to intersect. Is that clear? So adding time as an extra dimension here somehow simplifies the problem. Now, one of the most important principles we have learned in string theory in the past 30 years is what we call the duality principle. And this is, I think, one of the amazing things that is true in nature, and we don't have a deep understanding, but we have learned it's true. Which means that 2 things which look very different to the naked eye may nevertheless be identical. It's like a crazy thing, like somehow seamlessly going from one picture to a almost contradictory picture. They're the same and agreeing with each other. So let me try to give you an example of how this works. This is a drawing by Escher, and this exemplifies the duality that I want to describe. So here, if you were just shown this part of the picture, you will say, oh, this is just a sky in the day with the black birds flying to the left. If somebody showed you only this corner, you would say, oh, no, this is not about any day. It's about night and white birds flying to the right. Somebody showing instead down here, you would have said the opposite. It's nothing to do with the birds or the sky. It's actually just fields, the black and white fields there. But actually, as you can see, they fit seamlessly here, and they go from one to the other. So there's these transformations which kind of map one to the other, like flip them. And for example, the day here is being played by the role of the bird, and the black bird here becomes the night sky over there, and so on, and going up and down similarly. So this is a kind of a model or picture for dualities you can keep in mind. This kind of thing happens again and again in the context of physics, where little corners look very simple and different from each other, but they fit together in a seamless way, in a consistent manner. It's quite remarkable. So it's really amazing. So now if you look at here, before I do that, let's say. So this is the next puzzle. You have a meter long meter stick, and you have 20 ants. We love ants. We put ants on this meter stick, and these ants are going to move on it. Let's say they all move at the same speed, 1 centimeter per second, either to the left or to the right. If 2 ants get to collide, they reverse their direction and continue going in the opposite direction with 1 centimeter per second until they meet the next ant, in which case they again reverse direction if they collide with another ant. Is that clear? So they just collide back and forth and so on. Now, Unfortunately, the meter stick is not infinitely long. It's 1 meter, and it's held in the air, and so the ants fall off, unfortunately, at the end. They won't die or anything. It's all peaceful. The ants will fall down. So the puzzle you're given is where do you put these ants for the last ant to fall as late as possible, to survive on the stick as long as possible. So this is the situation. We have to look at these ants. They collide. The red goes here. It hits the blue goes there, orange, and so on. They flip back and forth, and they fall off, unfortunately, at the end. And the question is this: where do you put the ants, and which direction do you tell them to go, left or right, for them to last the longest on the meter stick? How many of you think the best strategy is to put the ants near the center and make them go in opposite direction? Raise your hand. There was one left, one right, one left, one right. Okay. How many of you think that we should just randomly put them, but make sure that they go left, right, left, right, left, right direction? Raise your hand. How many think it just doesn't matter where you put the ants? Okay. How many of you think it doesn't matter where you put all the ants except for one? Oh, none of you think that's, oh, a couple of you, okay. Actually, this turns out to be the answer. It doesn't matter where you put all the ants except for one. Why is that? Well, instead of giving you the answer, I want you to see the answer with your own eyes. You see, I tricked you here. I tricked you here by putting the ants with different colors. Ants are typically black, aren't they? And I didn't ask you for a specific ant surviving the longest on the meter stick. I said any ant, right? So all ants are the same for me in this context, right? So let's draw the ants as they are, black ants. Do you see what's happening? Does anybody see what's happening here? Are the ants colliding or going through each other? Actually, is there any difference? There is no difference. They're dual to each other. Whether you say they collide or go through each other, the ants where they are doesn't change. The totality of the ants are the same. The identity of the ants flips, but not where the ants are. So you might as well assume the ants are going through each other. The answer is the same. If the ants are going through each other, all you have to do is to put one ant at the very end of the meter stick and say, go to the right and don't worry about anything else. That's it. Again, this is the duality in the sense that you flip the identity of the ant each time you flip them, and that transformation changes the picture, but the answer doesn't change. Now, this is going to be my last puzzle, and this is actually my favorite puzzle because it teaches us about scientific methodology, how scientists think about nature. And it involves doing an experiment, and we're going to do an experiment together here. But what do I mean about the scientific methodology? I mean the following. First, in science, we do experiments. This is like examples. The second thing is that we formulate a general principle based on the experiments we have seen, formulate some property, some hypothesis, some law that try to encapsulate those things that we have seen. Finally, we come up with arguments why or how it works. Okay? Is that clear? So now we apply this to a particular experiment, and the experiment we want to do is the following. We have a circle, and we pick 2 points on it. How many regions we get if we connect 2 points inside the circle? 2. So in other words, with 2 points, we get 2 regions. That wasn't that fancy, but that's an experiment, easy experiment, no problem. Suppose we do 3 points now and connect all the points together, and then we ask, how many regions do we get now? Well, now we get 4 regions. 3 points, 4 regions. How many are we going to get with 4 points, you think? Anybody? How many? 8? Let's see. So this is 4 points. Let's count. Right? 8 regions. So in other words, 4 points, 8 regions. Are you getting the pattern? Okay, how many are we going to get with 5 points? Anybody? Exactly. So you see the pattern here, right? So what's happening each time? Each time you add a point, we get double the regions. That's the observation. That's the experiment. We write down this, notice this fact. It doubles. Now we have to, we come up with the formula, which is basically a factor of 2 to the power of the number of points minus 1. Each time we increase the number of points, we get one more factor of 2. So that's our hypothesis. But the question is, why is this the answer? Anybody? Well, let me not bother you with it, but let me just say one kind of thought that might go into it. You say, okay, every point you add, you introduce a line, and each line breaks the regions into left or right, so there's a factor of 2 involved. It's either on this side or the other side, so there's a factor of 2, big deal. Yeah, sounds good, right? So how many are we going to get with 6 points? What? 30? Huh, okay. Can you see I'm missing something here? Is there a spot I'm missing? Do you want to check it out? Huh, that's bizarre. My video guy didn't do the job right. Sorry about that. We have to go back and no, actually this is the correct answer. It's 31. It is 31. So we were wrong. Our hypothesis is wrong, and our explanation was wrong. An experiment clarifies that it's wrong. Don't believe me? Check it again yourself. You might ask, what about the 7 points? You might be itching to know if it's, how close is it to 64? Well, actually, it's not that close, 57. Say, okay, I want to know the real formula. Okay, there's a formula in this case. The number of regions is 1 plus n choose 2 plus n choose 4 for those who are familiar with combinatorics. So there's a formula. And this formula, if you continued n choose 2, n choose 4, n choose 6, if you added all of those, it would have been 2 to the power of n minus 1. But it stops here at 4. So after 6, it's going to break down because it doesn't have the right term missing. And it gets to miss more and more. So this shows that in science, we never stop experimenting. We always continue experimenting, and we always doubt ourselves. We always question our description and hypothesis and always look for more checks and checks and checks, and that continues in science to date. We never think we are done. In fact, in a sense, I personally believe none of the laws of physics we know today are exactly correct. They're good approximations, but none of them are exactly right. There's some things will change, most likely. Nothing is in the final form. So I hope I have conveyed to you the power of simple mathematics and that physics is fun. Physics is really fun in terms of these simple ideas, and don't let anybody try to convince you that this is complicated or this is that and that. At the bottom of it, there are simple ideas explaining even the most advanced topic like string theory, Big Bang, black holes, and all that. Thanks for listening.
Okay, thank you very much. And we have a little bit of time for questions. And you can ask questions about talk, but obviously any questions about life, universe, and everything are welcome. Okay? Ask anything.
Not anything, no, about physics.
Well, you have a right not to answer, but it's
okay, yeah, that's true. No. But please feel free to answer. It's nothing, we're very informal here. Anybody have any questions? Yes. Yeah.
Oh, okay, speak up.
I think, how would entropy play? How would entropy play into some of the principles that you were?
Entropy? Well, entropy counts the number of degrees of freedom a particular system has with given conditions like energy or something like that. So I did not talk too much about entropy here, but if I were to talk about black holes, I would have talked about entropy, for example. Or if I were to talk about thermodynamics of a gas or something in a room, I would have talked about entropy. But more interestingly, in the context of the things that I have talked about and the work I have myself been involved with, is a black hole. For example, we know that the black hole has an area, what we call event horizon, for which you cannot go inside, or if you go inside, you cannot get out. But actually, Hawking showed that no, indeed, black holes radiate, and it's like they have degrees of freedom inside, and the number of degrees of freedom of the black hole seem to be proportional to the area of this event horizon. And so using ideas from string theory, we showed with my colleague that indeed the number of degrees of freedom on the black hole can be recounted by the number of ways the strings or higher dimensional membranes can wrap around these tiny little spaces. So these extra spaces were useful in accounting for the microscopic degrees of freedom of the black hole.
Questions? Yes.
Okay, please.
Hello.
Hello.
I just had a question about in the picture of your string theory, in a proton, there's the two up quarks and one down quark. How come the down quark wasn't like a full string, but like kind of like a plane?
Yeah, I was just giving the options. I was not claiming it had to be like that. It was just a picture. There are different ways you can get degrees of freedom. So the string which is ending on that plane, those kind of planes are called D-branes. It's just a name, which means that they can cut open a string. So some degrees of freedom can be cut open by things like these, by these sheets, called D-branes, or some of them are just closed loop. So it could be open or closed. That's all I wanted to exhibit there.
Thank you.
You're welcome.
Questions? Please pass mic there.
Hello.
Hello.
I know before you said with the Higgs particle, that gives everything mass, correct?
Yes.
And with an antiparticle, is there an antiparticle to the Higgs particle, or?
It's, you can view there is antiparticle. There are some different charges. Some of them are antiparticle of itself in the context of the Higgs. So like photon is its own antiparticle. Sometimes it's self-particle.
Okay, thank you.
Are you still teaching that freshman class?
Yes, I just finished it this term as well. I teach it once a year.
In the
Now it's going to be a little difficult because the book is out
Right.
with the puzzles and their solutions.
Right.
So what I do at the beginning of the class is that I distribute free copies of the book to my students, but then I ask them not to look at it until I go through the chapter one by one.
Thank you.
But the good thing is that the students bring puzzles to the class, new puzzles.
First of all, thank you for the talk. It's fantastic.
Thank you.
A lot of my students are grappling with some particles having mass and some not having mass. So is that the symmetry breaking that you brought up? And of course, whether or not that's the answer, do you suggest a good resource for helping them to try to understand why some particles have mass and others do not?
Okay, good question. So the universe as we know it, we only know two particles that don't have mass, and it might be it. One is what we call graviton, which mediates gravity, and the other one is photon, which mediates electricity and magnetism. That's it. Every other particle has mass. That's what we think. It could be other things, but we don't think so. And the reason we don't think so is that we kind of have measured the properties of these massless particles because they create long-range forces. Like gravity, you can measure the force of gravity of the sun here. That's because graviton is massless. Photon, you can get the radio waves, you communicate with your friends across the globe. It's because it's massless. The other stuff are all boring and massive like us, so to speak. They cannot move faster enough. So this is the difference between them. So everything has a mass, except for those two. Now, there could be, in what we call the dark matter, there could be some other what we call dark photons, like the photon we know, but which interacts not with us, which is why we may not have seen it, but we don't have any evidence of that. So up to now, we only have two kinds of massless particles, photon and graviton. Now, all the other particles have mass, and every particle seems to get their mass of the ones we know through this mechanism I said, the Higgs mechanism, which basically means, so you have a potential like this, with the minimum, which is on a, I drew it in the wrong place probably because it's behind the podium. So you have a potential like this with a minimum, which is on a circle down here. So if a field starts here, it rolls down to the minimum and stays somewhere in the minimum. This is the analog of the person in the middle of the circle, which goes after the food. This is how it's actually realized in the Higgs mechanism. And it turns out that the masses of all the particles that we know, let me call this delta, all the masses are proportional to how far away we are from the origin. The proportionality constant will depend on the particle. Like electron has one proportionality constant, the quark have different proportionality constant, and so forth. All the particles we know get their mass this way, except this tiniest particles that we call neutrinos. These neutrinos are the lightest non-zero mass objects. They're very special, and physicists are trying to understand them better, and they might lead to clues, for example, about extra dimensions, and so on. So there's this puzzle related to these tiny objects, neutrinos, which have a mass like 10 to the power of 10 or something lower than the mass of these quarks. So they're really, really, really tiny in mass.
Okay. Yeah.
Thank you. This is referring to the last question I asked you about where you were talking about how measurements of, like, trying to measure the event horizon and such, and degrees of that. So would you say the issues with getting more and more in depth and the measurements changing as you get more and more detailed with with how you measure them, would you say that's similar to how, like, the shoreline paradox would work? I'm sorry.
What paradox works?
When you were talking earlier about how the measurements of, like, I believe it was the angle of an event horizon were changing as you measured them with more and more detail, like as they would get longer or shorter due to the strings.
Which part of my talk was I saying it?
Oh, sorry. When you answered my question earlier.
About the entropy you're talking
But
about.
the entropy, yeah.
Oh, yeah, yeah. But I was not about shorter or larger. Okay, so there's the entropy of the black hole, which is microscopic degrees of freedom of a black hole. I said were accounted for by things like strings wrapped around the extra dimensions.
Okay. Would you say that, like, would you say, like, the issue, you said when you were talking about that, with the issue with getting more and more detail and the measurements changing as that goes on, would you say that's similar to the shoreline paradox?
What is shoreline paradox? I'm not sure I know.
Basically, where it's a thing with maps, basically where as you get more and more detail.
Oh,
like,
no.
as
You mean
you
like
measure them-
fractals. No, this is not like fractals, you mean. No. It's not shoreline in the sense that you get more and more dimensions of higher dimensions when you get more and more zoomed in. No. It's nothing to do with that. So, well, okay. When I say it's nothing to do with that, the way I describe it had nothing to do with that. There is truth to the fact that we believe this horizon of the black hole is not necessarily as smooth as a sphere. And indeed, it's possible that when you get to the tiny scales, like 10 to the minus 30 centimeters, you will see more structure. Like, oh, it's not quite smooth, oh, it's a little wiggly, and so on. Similar to the shoreline issue that you're mentioning. So there's most likely that possibility. And indeed, people have speculated that these degrees of freedom that I'm talking about has to do with these fine structures on the surface of this horizon. But nobody has measured it that way. People have suggested it because the entropy is proportional to the area. So they say, oh, maybe there are features on this area that accounts for this.
Thank you.
That's a good question.
Okay, thank you all for nice questions, and thank you for answers. Let us thank Cumrun again.
Thanks for everybody coming.
And if you have some amazing puzzles, you can send a message and